Good everyone, my name is Graphics. In this video, we want to solve a problem involving steady flow energy equation, and the question goes like this. It says air flow steadily through a gas turbine at the rate of 5 kg per second. At the inlet to the turbine, the specific enthalpy of the air is 2975 kJ per kilogram and the velocity is 60 meter per second. At the exit, the velocity is 100 meter per second and the specific enthalpy is 2250 kJ per kilogram. Determine the power developed by the turbine, assuming the turbine to be well insulated. Now, in this kind of question, the first thing you have to write is your what? Your parameters, right? So we'll be writing what? The parameters. The first thing here is the mass flow rate. We are told that the mass flow rate of the gas turbine is 5 kg per second, right? So when the air flows, it flows at a rate of what? 5 kg per second. That's for the mass flow rate. Now the other one is the enthalpy at the inlet. Since we say inlet, meaning we'll be using a subscript of what? Of 1. So it says the inlet will be using for enthalpy, we use H to represent enthalpy. So I'll be writing H1 because we are told that it is the inlet. So H1, right, is given as what? 2975 kJ per kilogram, right? And the next one here we have is getting us the what? The velocity. Now I'll be using C for my velocity, not M, right? I'll be using C for my velocity, not V. Is that okay now? So I'll be using C subscript 1, showing that velocity at the inlet, right? And that's equals to what? 60 meter per second. And similarly, at the exit, we're told that the velocity is what? 800 meter per second. So I'll be using C sub 2, right? To show that it's exit. 1 for inlet, 2 for exit. Is that taken? So C2 is giving us 100 meter per second. Now the specific enthalpy at the exit is giving us what? 2250 kJ per kilogram. So I'm using H sub 2. Is that taken now? So we have to look for what? The power developed by the turbine. So the power developed by the turbine is represented using the word the work rate, right? So my power here is what? The work rate of the turbine. So I'm using W and a dot on top, and that's what we're looking for, right? So we'll start. Now recall, we know that the power developed is given as the work rate, and that's given as what? The mass flow rate times what? The work transfer, right? So that's what we term that equation what? Equation 1. Now there's something you need to understand. From our parameters, we have the mass flow rate, which is 5 kg per second, but we don't have the work transfer. So what you should do here is for you to look for the work transfer, right? Now the steady flow energy equation for a turbine is giving us the enthalpy at state 1 plus the kinetic energy at state 1 plus the work transfer equals to the kinetic energy at state 2 plus the enthalpy at state 2. Is that okay now? So if I make my work transfer the subject of the formula, I'll be having my C2 I'll be having what? My kinetic energy at state 2 minus kinetic energy at state 1 plus enthalpy at state 2 minus enthalpy at state 1. Is that taken? And what is the formula for kinetic energy? It is what? Half C square. We are not using V, we are using C to represent our velocity, right? Where the C is the velocity. Now what we should now do here is this. It will now give me my C2 square all over 2 minus C1 square all over 2 plus H2 minus H1. Now I am not using the M because I'm dealing with what? Per unit mass, right? I'm dealing with what? Per unit mass, that is intensive properties, right? So I'll be having this will now give me C2 square minus C1 square all over 2 plus H2 minus H1. Now, if you're wondering how I got all these things, you can click on this link at the top right corner to give you more explanation on how I come about the steady flow energy equation. Because in a turbine, we have no heat input. Actually, the equation has said it is perfectly insulated, right? And we have no potential energy is what is neglected. So if you click on that link I showed you earlier to give you a better understanding on what I just said here. So we said that the W12 here now will now give me what is my C2. C2 is 100, so that will be 100 square, minus C1 is 60 square. They will all over what 2 multiplied by 1000. Why am I putting 1000? Because the velocity on its own is in meter per second square, while everything is in kilo here. So we need to make the unit to be what? To be uniform, right? So plus H2 is 2250 minus H1 is 2995, right? So this will now give me 100 square is 10,000 and 60 square is 3600. 10,000 minus 3600 will give us 6400. All over 2 times 1000 is what? 2000. Now if you subtract 2250 minus 2995, you are going to be having minus 725. Are we together? So from here, if you divide 6400 over 2000, you'll be having 3.2. So we have 3.2 minus 725, and our work transfer will now give us minus 721.8 kilojoule, right? So we are going to input this value into equation 1 above. Is that okay? When you put that, we have our work rate will now give us the mass flow rate times the work transfer. I will know my mass flow rate is given as 5, right? Then you multiply it by the work transfer, which is minus 721.8, and this is going to give us minus 3609 kilowatts, right? So this is what we have gotten here. And if you have found this video helpful, please don't forget to like, subscribe, and also share the video. Thanks for watching.